Yeah, so RNN is mostly used for sequence modeling. Um, so here we can think of codes as a sequence. Um, so let's say it can write, let's say, C code that at least is syntactically correct. So at least it compiles. But the modern day like sequence modeling architecture like transformers, they, as you know, some of you are using ChatGPT already to write code, right? So it also writes meaningful codes now. So these are a little bit, RNNs are a bit old now, but the ideas and all this could be keep getting used also in some form. It can write text. So basically, again, text is a sequence model. You have a couple of words and then it needs to get completed basically. So next word prediction and so on. So we can think of text as sequence problem. And it can write, let's say, papers maybe, not yet, but syntactically correct paper. It compiles in LaTeX, let's say. For speech also has sequential nature. So it can be used there. Stock market prediction also has the sequential nature. You observe some stock values for certain listed company there, and maybe you would like to predict. So these are sequential modeling problems where you observe something, some past data, and you feed the current data, whatever you observe as an input, and then your predictor will try to predict the output for the current time. And you can keep doing this. As you can see, it's a kind of a sliding window. There is a bit of similar idea that we saw in CNN. But here we look at the past history, okay, to predict the current. So so we can model this mathematically like this, where yt is the current prediction and it looks into previous n of the x values. So in this case, these are the previous x values, and based on that, it's going to predict the. So here you can say it's yt that comes out from here. Okay. So ideally, you would like to look into all the past history. That would be the optimal case. Like, why should you forget something that was very old? But as you can guess already, using long-term history is really not computationally possible, feasible, right? So number of parameters increase, and we cannot afford to keep everything in memory and so on. Okay, so in the case of stock market, we have quite a few historical data. It could be news, it could be some event, it could be news, negative news related to the stock, and that can kind of affect the prediction. So can we build a network where current output influences all future times? So as we know, it has to be some kind of a recurrent idea. I mean, you cannot really save everything from the past, right? So here we cannot really afford to save everything from the past, but yet we want influence of those past to predict the current future. I mean, to current the present, let's say. So it has to be some form of a recursion, as you can already guess. So we say yes, but then it has to be some recursion. So storing all xi is not feasible. Make the output depend on the previous output. So this is the recursion I'm talking about. That one possibility is that current input xt, and then the output from the previous prediction that could be fed in. So we expect that this output somehow encodes all the useful past information. Okay, there is a tremendous amount of load on this variable yt to encode all the past data, useful features, but theoretically we can say that, yeah, yt somehow captures everything that it has seen from the past. xt is the current one, and that can be used to predict the current yt. Initial, you can define it to be some initial state, because at the end of the day this will be parameterized model by neural network, and it will get trained. So input x naught at t equals to 0 produces y0. So that's the notation. Y0 produces y1, y1 produces y2, and so on. And this is the model that we can think of. So yt goes in, and then the xt, the current input, goes in. So this is how we see RNNs. Okay. And these blocks that you see here, these are some MLP. Okay. Some feed-forward network, multi-layer perceptron. It can be, however, complicated. It depends what you want to do with this. Color coding, we will see why some are green and some are orange. We will see that. But the elementary idea would be like this. YT, as we know, YT somehow encodes all the previous useful information, historical data, okay, and that is fed in here. So we can do this recursion. We can unfold this over time. Time here refers to maybe, let's say, next word. It could be, or even next sentence, depends what you want to do, or next word in the speech, or so on. So this is basically a recursive thing, so no need to explain. So this is just same thing repeats again and again. So so the current output needs to, what is the problem in the current model is that the current output that you have, for instance here, and it is used as a way to kind of store everything from the past. So current output needs to store history of infinite past. So this is the current problem we have in this architecture, and can we modify this further? Again, we can go back to the previous approach, like in the most brute force way. We can say that all outputs can be taken, all previous outputs can be taken, and not just that, all the input data could be taken. So we already know that this is not something feasible anyway, right? So our problem is that this YT that we take, and this is the previous one. Yeah, of course, here we are saying that take everything. So both are like extremes. So I just take one previous output. That seems like YT has to store everything from the past. And another possibility is to take everything, all the previous outputs. That's also not feasible thing. Similarly, we cannot take all the previous inputs. So we want to find a middle ground somewhere between these approaches. So we call this complete Knox network autoregressive. That's the term used for architectures that deal with sequential data, time series data. So it's autoregressive because it's feeds the current output that is used for the future predictions. So that way it's like autoregressive. Okay. So memory of the past is in the output itself, not part of the network. What if we introduce explicit variable for memory? So that's where the concept of memory came. So can we define memory abstractly? Yes, we can do something like this. So we have yt minus 1. So this is the memory variable mt. This memory variable itself depends on the previous output yt minus 1. Some variable ht minus 1, we will make it precise, and mt minus 1, which was the previous memory variable, okay, previous time memory variable. So we will make it precise. So this could be one modeling, that we want a memory which is separate from output. Of course, it depends on the output and some hidden state like ht and the previous memory. But we want to model it. We want to abstract this out as memory variable. Okay. So HT is the hidden state. That will be clear from the figure that we will see. So HT depends on the input xt and the memory variable mt. Okay, and then the future output could be given as yt is some g of ht. So we may see like this. So what we plan now is to have a memory variable that goes across like this, across time. Some memory is preserved, okay, and this memory could be used as a in the output. Okay, so this is our abstract framework where we want to see hidden state and which uses the memory and so on, and memory and this the current hidden state is used as output and so on. That's fine. But if you go to very early ideas, then very old ideas were like this, where they thought about memory, but memory was just copied over. Okay, that's not exactly following this way that we plan to do, and like this is the modern variant. So if you reflect a little bit on the very old ideas, they had some new variable that used to get copied and used in predictions. So this was like simple explicit copy of something which is useful, let's say. Okay, so this was called Jordan network. A memory unit keeps a running average, and here the parameter mu in the memory has no learnable parameters. So there was no learnable parameters along this direction. It just keeps an average. Okay, so. And then came Elman network. Elman network says that this green block that you see now, now this color coding will make sense. What this says is that just copy over this hidden state and use that in the prediction of the t+1 step. Okay, so so basically you have multi-layer perceptrons in this direction, right? So you have input, it goes through linear combination activations, and then another block linear combination and activation, and so on. So what it says is that intermediate output that you get, that may hold some useful features which may act like a memory. So why not just copy that over and then use it in the next time step. Okay, so remember previously we were saying use the output along with the input and then produce the current output. Now we are saying let us use hidden state as a form of a memory that we just copy over. So again, the one here indicates that it's just a simple copy. There is no weights along this memory channel. So basically this means that that during training we won't do any backprop along this direction. So just copies the previous hidden state. Assumption is that the hidden state encodes the information required and so on. So that's like we assume that some useful features has been kind of saved in these green blocks and that could be used. So we can write our model like this because we use hidden state itself as a memory. So we kind of remove that m variable because h itself stands for like memory for us. So let us kind of use that. So this is our current status of the sequence model. So here we have some initialization of memory, and then you have the current input xt at time t equals to 0, current output, and this hidden variable ht is then just simply copied over at the next time step and so on. Okay, and so that's like the simplest RNN you can think of. Okay, so of course, what we could have done also is to put weights along this direction, memory direction as well. Why not just put weights here, right? Not just use this directly, but let us say some weight here. So the output that I get from here will go through some linear combination and activation as well. Okay, so these linear combinations are with weights, and so obviously these weights can be trained as well. So basically what we're saying is that rather than just copy, why not, because this is anyway a supervised machine learning model, so why not let the network learn what is useful to copy from previous hidden state to the next hidden state. So once the weights are there, the network itself will try to figure out that explicit copy was good or some other combination of the memory was good. So we can extend this idea also to two-layer network. So in this case, as you can see, there are now 2 memory channels we have. So we can just extend these ideas with 2 memory channels. Okay. So we can have more complex connections on this. We can have skip connections like the ResNets we have seen. You can just take this via identity map and just add it here. So this will act like residual connections and so on. So one can play around with this architectures. One can also go with this approach, where the hidden state of the first level is also used at the hidden state of the second time step. Okay, and similarly the second time step hidden state for the previous time can be used in the first hidden state of the second time step. Okay, so basically these arrows tell you everything, how to mix and match these. So we can make it like more complex like this. So we can also think about second order, even memory. We can think of this in a way that why should I just pass memory to only the second time step? Why not I also propagate it to the third time step? So you can also play around with the time, how your current hidden state, which you see as a memory, how it can be propagated also not just to the next time step, but also to the previous time step. I mean the next to next time step. So all these things are possible. You may try, but usually simplest models are preferred, because if it works well, that's fine. In RNN, shorthand notations are used like this. This means this is a shorthand, meaning that there is only one inner hidden state here by the green block, and you basically should know how to unfold this. So if you unfold this, then it looks like this. Okay. So this is like short form you see in the papers. Okay. Similarly, you can look into this, and then if you unfold this, then it looks like this. And then if you unfold this guy, then it looks like this. Okay. Mathematically, what RNN means is there are some calculations obviously that goes inside these blocks. So we can have a quick look into these blocks. So let us try to understand this simplest RNN form. So X is our input and Y is our output. Okay. So let us see what happens with the X. So we see X here. So this X goes in from here, and this gets a weighted combination with the X. Okay. So these weighted combination happens via here, and then this H t minus 1 is coming from the left. So that's also a vector, and we do a weighted combination of that. So that from here we have this. So this is our X. This way we are going through this Xj. So X could be seen as a vector x1, x2, xj, and so on, right? So we have to do a linear combination of these guys. So then this will be this will be this guy, right? It goes through all the inputs, and so basically this is our X. This is MLP only, which is the notation thing. So this is our input, let's say, and this is going to these neurons, right? So this is the linear combination that is happening, right? And similarly these, right? So these weights that you see here, these will be Wji, and since these weights correspond to this first layer, we call it zeroth layer. Okay. So this linear combination that you see here, that's doing this Wij 0xj. Okay. And this from here, from the left hand side, you have the h variable that is coming from here, and h superscript 1 means the first level. Okay. So you see level like this. Okay. So 0th level, 1th level, first level, I mean the second level, and so on. So 0 level weights, that's why they were denoted by W superscript 0. These memory channel that you are taking now, we can call this H superscript 1. Okay, and since it's from the previous time, we call this T minus 1. So they themselves are vectors. So these we can see these as H1 T minus 1, and then first component as a subscript H1 T minus 1 subscript 2, and so on. So these H that you see here are being used here. Okay, and obviously we want to see this as a weighted combination, so that those weights we call it W1 1, and so this is again going via MLP, right? So again these HT minus 1 is being used, and this is going into some neurons here. So this is our HT minus 1. And we are doing a linear combination of these guys here, right? So The notation W11 means basically in the current form what we're saying is like this memory channel that we have is HT minus 11 is only used in the first level, okay? Because if you see the diagram that we had before, there was a proposal to also use some cross connections, right, like this. So there was a possibility like this. So the fact that we are using this for the moment, we will call it 1 1. But then the weights that will come via this way, this will be 1 2, right? And then these guys that go, this will we will call it 1 2, I guess. Yeah, and this will be 2 1, and this will be 2 2. Okay. So this is why we had this we have these notations. Obviously, you could say, what if I have one more? Yeah, then in that case, we will have 3 indices to capture this, right? IJK, W superscript IJK. So, but usually, as I said, when we usually work with simple models like this, and so via this we did linear combination and activation, and obviously, as usual, we add the bias terms. So this guy X that went in had a linear combination. This guy that went in has a linear combination, and then we had the bias. And once we had the whole linear combination, and then we did the activation by F1. Okay, some activation function, it could be sigmoid, 10H, whatever, depends on the problem. Now you had this H1T. So that the output that you get is now the output that you got here is H1T. Okay, so this is the H at the first level at time t. Now this will be this will go through linear combination and activation now. Okay, so same process, H1J. This is the linear combination here with the weights at the 1 level, right? So remember, here we use W superscript 0, but now here we are using W superscript 1 because these are at weights at this level. And then you add the bias term again, and then you do the activation of these guys. Okay, and then finally you get YT at this step. Okay, so this is the RNN. Basically, that's all about RNN. You can just add one more block like this here in this case. So you have the second block as well. Essentially, the idea is recursive. You the XT goes in with the weights at W0. So this is our W0, and then the H1 came in. According to this unfolding, we see that H affects H1 will affect H1 at t plus 1, right? So that way, this is how we have to do H1 at t minus 1. H1 t minus 1 will be doing linear combination with the weights W11. So this is W11, and then the output from here will be fed in at the next level to get H2. So then again, the output that we had here, it is going through linear combinations. And these are the weights W superscript 1 here, and then you are accessing memory at the second level as well. So this comes from H2 t minus 1. So this guy goes through linear combination and activation with its weight W22. So these weights W22 are going here. These weights W11 are being used here, and then you have the bias terms, and then finally the H2, the output that you get here is goes through linear combinations and activation with the weights W2 here. Okay, so as such, as you can see now, the idea is kind of recursive. In the code, it just does these things recursively. So this is the basic RNN that will be useful when we go for VQ VAE that we want to continue from where we left. So some of the initial intuitions are through this RNN, so that's why it's good to know a little bit about RNN first. Okay, so yeah, one could go for a little bit of skip connections as well, right? So these are like some additional skip connections kind of thing we have added here. So here also you have to just modify a little bit. So linear combinations happens here, and then so here there is no change in the first output H1, and then when you go to the H2, then basically you will have you see you have direct access to also the input. This weight will be W02. Okay, this arrow that goes here. So that is being reflected here, and the other things are kind of same. And similarly, this arrow that you see here, that is for this guy, W13. Okay, this is doing this skip connection part. Okay. In this case, it's not just an identity map. It is the weighted combination that we are taking in this case. Okay. So these are calculations for RNN used for sequence modeling. Now, depending on the problem at hand, you may want to use the configuration of the input and output. Okay. So in the simplest case, it could be 1-to-1, depending on the applications at hand, right? So it could be one-to-many. So I mean, it could be, let's say, image, and then these are the captions. So captions could be seen as sequence of words. So given an input image, you may want to generate captions for that. Okay, it could be many to one, let's say sentiment analysis, something like that. So a bunch of one paragraph is given, and based on that you may say what this paragraph could be, whether it's something positive or negative. That could be one possible output. Okay, so there are many applications. Based on that, you decide which type of input output approach you want to have. It could be many to many. Language translation could be many to many. So you can have one whole sentence of English, and you may want to produce some German, let's say. So that could be like this, and so on. So okay, so I don't think I will go into back propagation of RNN. It's a bit tricky. It's called BPTT, backward propagation in time, but one thing that you should remember in RNN is that when you see RNN like this, the network doesn't have different weights for different time. Okay, it's the same network basically. Okay, so it is the same network, just this is a snapshot of the same network at this time. By same, I mean the weights are the same. Okay, so that is critical. Okay, so this weights 0 that was there is the same weight 0 there. So basically it's a shared parameter network. So that will have effect when you do the back propagation. Obviously, when you do the back propagation, it will go through the time, and whatever changes that you incurred in the current output, that will get added up. So W0, while you are going backward, W0 will keep getting updated by through this. Okay, it is the same W0, but until here, whatever W0 you had while you do the back prop, now this W0 got updated again. While you back prop at this time step, the same W0 got updated. Okay, you are not saving W0 for different time steps. It's just that while you are going back, your W gets updated each time, and same is for all the weights. W1, the one that goes through the memory, in this case W11, they all get updated. So it's a bit tricky to explain this. It can take the whole class. It can take more or less kind of whole class. It's a implication of the chain rule, and also obviously the loss function that you define, whether it was 1-to-1, 1-to-many, and that also defines how the training happens in RNN. Okay, so whether you are going to wait for the time step t and then evaluate the loss, and then you will be able to do the back prop. So how often you compute the loss, that also decides how to do back prop. So training is, as I said, it's kind of complicated. It uses this chain rule and so on. It's in the slide. If you need this, you can use that. But without going into the detail, what we see from all this is that the chain will get very big. Okay, so without going into detail, at least what we know is these are deep. We can see this as deep in time. So basically, when I take the gradient, due to chain rule, it will be a big chain. Okay, so we will see that. Okay, and one of the variants of RNN is that you may think of bidirectional RNN as well. So basically, what this is like you see in both directions your sequence of words goes like this, but your sequence of words can also go like this. So basically the same sentence you reverse and pass it from last word, second last word in that order. And obviously the normal one is that you pass first word, second word, word, and so on. So that's called bidirectional. So sometimes it helps if the network sees. So you want to do language translation. So let's say I'm going to market, but you will pass in both ways. I am going to market, but then you can also pass it this way: market to going MI. So sometimes this helps when you also pass the reverse sequence. Okay, of course you cannot do this in all type of problems. Okay, because I mean few things are causal kind of. So you may not want to do this in all kind of apps, but there is a concept of bidirectional RNN, and then basically you feed them. And then you have the weights and so on, and let the network understand, right? Because it's anyway it's a supervised learning, so network will use it in whichever way, whether it's a reverse sequence, whether it's a forward sequence, it will learn it in a good way. Okay, and finally it has to translate this to some French, let's say. Okay, so you may not want to do this in general. So this is the view of bidirectional RNN, right? So sequence, there is an arrow that the time component that goes like this. So here, I mean here this way, and then you have this way. Okay, these are the arrows which are reversed in this case. So first you start with xt minus 1, and then in this case x0, x1, and so on. Okay, and you have these connections, skip connections, so on. These are weighted and so on. So I mean some prominent networks came via this. Okay, so summary of RNN is that RNN is for time series data, and if you have applied, let's say, MLP to add two binary digit numbers, then obviously an MLP is not a good idea in this case, because we know that when we do binary digit binary additions, then we know that we kind of go sequentially. So we look at the last two digits. So this could be the input to RNN, and then the interesting part is the carryover, right? So here also we add these two, so there is no carryover, and here third digit, then the fourth digit, and then the fifth digit. I guess in the sixth digit there is a carryover, 1 plus 1, and then there is a 1 that should carry over. So that will be the memory that you are looking for in RNN. So that should be the interesting memory, the carryover when you add two binary digit numbers. What is interesting to propagate, that is kind of evident in these binary digit additions. If you use MLP, then MLP does not encode this sequential nature, and you may have to give many lot of data with lot of permutation of these digits, so that it can make sense of this. So sometimes the architecture design is essential. Just like in CNN we saw, it was kind of rotation invariant and translation invariant. So then the convolution was a good idea there, and for sequential problem, the idea of carrying over some memory and all this makes sense. Okay, so this is the thing that we said. So I mean syntactically, at least it was doing something. So one of the problem in RNN was something called vanishing and exploding gradients, and that is seen when we are training these deep. We can think of this as deep because it's deep in time. So when I do gradient propagation, it does look through all the time steps. So in that way, computing the gradient via chain rule will lead to. So there is some instability analysis and so on, which we will skip. Basically, so there are these instability analysis and so on, but I will show you the main result, why. So there were like people did a lot of analysis because RNN had difficulty in trainings, and people were trying to understand, and the problem was this vanishing and exploding gradient, and there was some ideas on like maybe it's which type of activation functions you use, that also has some effect. So I believe TANH was kind of the proposal, which was kind of more stable, if I remember. So Yeah, so this is a vanishing gradient in general is a problem of deep neural network because they are of this nested functions are there. So if I am going to take the gradient, then gradients look like this or like this. So these are like product of so many gradients. So if the gradients are small and let us say weights are also kind of small. So by small we mean, let's say, even 0.1 in norm, right? So values are kind of 0.1 and so on. So if you keep multiplying these guys 0.1 again, less than 0.1 again, and so on. So basically at some point it will go very close to 0. Okay, so it will go very close to 0. This means that during training you do not get any gradient information, and the weights that you update, usually we know that weights are updated via gradient descent. So these gradients are 0, meaning weights did not get updated, right? So these are the problems with the RNN. We can also do it in with Jacobians and so on, but yeah, this is the point. Okay, so this constantly shrink the derivatives and so on, and then at some point it will get forgotten. So these are the issues. So you see, they plotted the results of what is the signal that they get via gradients, and as you can see, only after 10 layers, only up to 10 layers, you could see the gradients being non-zero. But beyond that, and so this means that as the network goes beyond 10 layers, you hardly get any feedback. So this means that this vanishing gradient in deep neural network architecture is quite significant. Okay, so they plotted these values of the weights and saw that you are hardly updating the weights beyond the 10th layers. Okay, so it can happen in like a reverse way. So you can say that this is the 100th layer. So your gradients maybe are valid until here, but for the gradients for this layer weights, they are kind of like now very close to 0. Okay, so these weights beyond, let us say, the 90, less than 90, while doing backprop, these guys are not getting updated because they have to come through this. So these are the problems, and then yeah, so these are the same things being explained in a little bit more detail. So we can skip this for the moment. So then there was an idea of then there was an idea of what could be done if this is the case. So and one of the things that was for vanishing gradient was that we were losing out, let's say, on the memory channel as well, right? So there were some ideas that can we keep the memory channel kind of separate from the weight updates. So there were ideas like this where this separate channel was kind of introduced, and across this channel there were no weights. So this means that that I may update the weights through the MLPs of the RNN, but I will not touch this directly. Okay, indirectly I'm touching because I'm going via this, right? And this sigmoid is using the weights. So let us say this is first layer. So indirectly I can say that I'm updating this, but not across the channel. Okay, so this was an observation that if we can keep this memory separate, it could be. So these were some of the ideas, and then all these ideas compounded into something called LSTM, long short-term memory. Okay, that's the name, LSTM. So that has taken over RNN these days, and this is like RNN. So you can see this is a RNN block, but inside this, the way things are done is now very different from RNN. So this is the RNN block. So XT goes in, and then some HT comes out, and then this HT is used here, and then some XT plus 1 is used, and so on. And there are some notations like pointwise operations, vector transfer, concatenate, copy, and so on. So these are being explained here. But what is interesting is this memory channel that you see in the red block, that is without any weights. Okay, so that was the proposal. So we call this like the cell state and so on. And so gates are usually sigmoid and followed by pointwise activation, like in this case. So LSTM block can be decomposed or seen as 4 separate modules. The first module is forget gate. So this is defined explicitly like this: sigmoid of WF, which is the weights of HT minus 1 XT plus the bias of this. So the whole goal of this block is to do this computation. Forget gate determines whether the memory V is shrunk. It does that by looking at the input xt and the previous hidden state ht minus 1. Forget gate looks at ht minus 1 xt and outputs the number between 0 and 1. So there is a sigmoid there. So self state might include storing gender so that the correct pronouns can be used. Let's say, for example, so when we see a new subject, the forget gate would indicate the forgetting the gender of the old subject is required. So it will try to forget. And these are hypothetical. No one has really checked this explicitly that this really happens. So some text were carrying over some info on some gender. It was about some male related thing, and then the next set of sentences that started goes with the next gender, let's say female. Then it has to forget the male related pronouns and so on. So this is hypothetical. I have not seen anyone kind of checking these things explicitly. Then we have a concept of input gate. So you will see all these gates combined. So previously this was this forget gate. So now we are looking into the input gate. So input gate explicitly is defined like this. So we know what is xt, we know what is ht minus 1, we know what is the bias. So you do the sigmoid of these, then you get this it you, and then you also produce this c tilde t, which is some intermediate variable, and ht minus 1 xt, and you add the bias and so on. So input gate essentially produces 2 outputs, it and ct. Okay, and then we have the memory update gate, and this memory update gate is ct. So ct is a combination of ct minus 1, the previous ct minus 1, and the current ct tilde that you computed here, okay, in the input gate. So it takes those, so this is the it that it takes. Basically the input gate has produced these 2 things, it and ct minus 1, and then it also uses ct minus 1, this guy from the previous channel. So and then finally it adds those values. So this is the memory update gate. So as you can see in the memory that we have, or we also call cell state. So we have this ct minus 1 leading to ct and so on, but they themselves don't have any weights involved here in the middle. Okay, they are independent of the weights. The proposal was that memory should be untouched from direct weight updates. Okay, and that helped LSTM kind of preserve memory for longer. And then we have this output gate. So in output gate again explicitly we have linear combinations with the xt and then some bias term, and then we do 10h of the ct that came from here, the memory channel. Okay, so that's it. And then the OT that we computed in the previous step is also used as a pointwise vector multiplication. Okay, so all this looks very hypothetical. There is no real explanation, I would say, of why one should have these gates and whether these really mean the way they are said to be. Okay, so someone played around with this. It's basically engineering. You played around with this and it worked, and people started using it. Just like transformer architecture, there is no real maths behind that. They just played around with some key value ideas and it just works. Now people are trying to prove things, but the way it started, there was no meaning as such. So this is the LSTM. There are some like minor changes as well, but this is the full LSTM. So forget gate, input gate, output gate, and then you have this memory cell states being computed here. Okay, so and there was a small change to this, which is called GRU, gated recurrent unit, which basically is a simplification of LSTM. So now this is popular because it's less computational steps are needed in this case. It's a simplification. Some redundant things in LSTM was removed, and you got this gated recurrent unit. So that's it, and people have played around with grid variant of LST, like 2D layout of the LSTM blocks. So 2D grid LSTM, you can make it 3D and so on. So these are like one can play around with these things, but for our purpose it's okay. We know about RNN, we know about LSTM. LSTM was introduced to prevent gradient issues basically in the long chain rule. and we have GRU, which is more latest version of this. So now we have these basic sequence model. I am planning to cover a transformer as well, but a bit later. So we were here and we were looking into the VA engineering. What we have is VQVAE, so vector quantizations that we want to see today, and some issues with VAE that I will cover first, and then I will go to VQVAE. Then things like motion generation, even video creations, audio compression. So VQVAE is a very powerful idea. It's a simple idea but powerful, because it's simple in the sense like it goes into discrete latent, but then with discrete latent you can play around quite a lot. So in VQVAE, some of the issues are just like GAN. We saw some issues. It's good to know some issues with VAE. In fact, I would say this is not essentially only for VQ. For vanilla VAE also, we have this issue, something called posterior collapse. So we remember this this VAE objective that we wanted to kind of minimize or I mean maximize. So this was the lower bound, and we have maximum likelihood estimator, and then this was kind of the L was the lower bound. And what we said is that MLE estimates are not possible, not tractable. So we created a variational lower bound, and then we said let us maximize this. So that's the thing that we already saw in the previous classes. So everything depends on this. So this was reconstruction error. So basically this is like this: X, the real X, and the reconstructed X. So it checks for the reconstructed accuracy. Okay, so that's the reconstruction error, and this is the KL divergence that tries to match the encoder distribution that is trying to produce the random vector Z. Okay, and then we compare it with the standard normal. Okay, so we kind of enforce this equality. So this is the loss that we. And basically VA tries to, it should be max, right? So VA tries to maximize this loss. So what was observed in some of the papers, or many explanations were given. So in this paper in 2019, they said the global minima of these correspond to optimal recovery of real data. So of course, when we look into this optimization problem, our goal is to kind of solve this optimization problem as well as possible, right? So ideally, when we see optimization problem, then we think of a global maxima, right? Or global minima if I change the objective to negative and so on, right? So ideally, obviously, I want to find a global solution for this, because as such it's a non-convex, so it will be like this, right? So ideally, if I have to do max, I will go for this guy, right? So theta star, phi star. So it's a non-convex. Ideally, I would like to go there, but usually that's not the case. In fact, finding a maxima in an optimization problem for a non-convex is NP hard. Okay, so there are examples like that. So in general, in general, you will usually settle for some local minima like this, if you can get hold of this. So you initially you will start with some random guess. Let's say you are here, then your gradient descent or ascent will take you to this local minimum only, because after that the gradient becomes flat, and you know that gradient descent is like W minus grad f. Let us say in this case is L, right? So once the gradient becomes flat, because it will follow the gradient direction. Once the gradient becomes flat, there is no way you can update your weights after that. So there is no way that you can go ahead and fetch your global maxima again. You are kind of stuck here. So gradient descent will lead you to local minimum only. Okay. So then this paper kind of try to say or give some ideas behind that. They do not completely kind of They do not give the full rigorous definitions, but then in very, very special cases, special assumptions on the function and so on, they said that if you indeed go for the global minima, then it gives you optimal recovery. So in our case, recovery was x minus x hat. So this is the reconstructed. So this is the whole idea, right, for VAE, that that we want it to reconstruct the image, because that's part of the loss as well, right? So we want it to reconstruct the image as well as possible, optimally as possible. However, in practice, VAE are prone towards converging to degenerate solutions. Okay, so the solutions that may not be optimal. Okay, so in one of the cases, what might happen in VAE is this guy. So you see, this is the encoder, and encoder basically it kind of, so if you look into the KL, the best possibility is that Q phi z given x becomes pz exactly, right? But that will be also a troublesome, because then you ignored x kind of. Okay, your encoder has learned to produce pz disregarding the x itself, but the point was that encoder should take the features of x and learn to map it into a proper normal distribution. So if it happens that it completely ignores x, the role of x, that's called posterior collapse. Okay, so some of the so in these papers they said, okay, it is because of the local minima and so on. So in some papers they say, okay, if KL goes to 0 directly very quickly, that's a problem. So they go for annealing type of approach. So we will see that. So one of the early uses of VAE, or the extension of VAE, was for sequence modeling. So they used RNN there. So as you can see, this is RNN, but it's a kind of the way it's written is slightly different here. So here you can see the input vector xt that goes through this this hidden state, and then goes through some output, and then it maps to this zt. Okay, and so basically you see this as encoder, and from here to here it's a decoder. Okay, and it is RNN type because we go by sequence to sequence. So now we take the next x t plus 1, and then it goes through this block, and then it learns to produce some z vector, and then it tries to reconstruct back the input. Okay, so some of the earlier adaptation of VAE was for sequence text generation, let's say. Okay, even audio generation. So some of the papers I listed, they also show results for audio. So this was reported in this paper. So posterior collapse was not reported in this paper, not until then. Okay, so this issue was found a bit later. So then you see the list of papers that tries to uncover this these. Okay, so posterior collapse for us is this problem. Okay, when the encoder becomes just pz. So possible remedy that was proposed so far is using some form of warm start, or using some penalty for the KL term, and then some papers looked at tighter bounds on the log likelihood. Obviously, I'm not going into detail of this paper. I'm just doing hand waving, but I will look into some of these. So it's not possible to kind of look into all of them right now. So some looked at more complex prior distributions, so maybe more than normal. What we saw so far is that we are enforcing normal distribution, but what if you go for more complex priors? So go away from maybe simple normal distributions, maybe. Okay, so modified decoders. So is it the problem with the decoder, and is it a decoder issue? Disallow prior from ever equaling the variational distribution, and understanding posterior collapse in general is still a kind of open problem. Although various works have looked into this, but there is no complete in the practical setting there is no complete resolution to this, but then there are some heuristics that people use in practice. So some remedies, although quite a few remedies have been proposed, so we are not going to all of them. So again, in the context of using VAE for text, so the Baumann in 2016, when they were studying this VAE for text generation, so as you can see now, the encoder for them is all RNN, or as I said, RNN are replaced by LSTM now, but we also call RNN as LSTM sometimes, like because they belong to those similar class. Okay, so basically these are kind of RNN. So encoding blocks are there, which are LSTM blocks, and these produce the mean and sigma, the variance. Okay, and based on those mean and variance, you get some sample Z, and from those sample Z again the decoder picks over from there. So this is our decoder and this is our encoder. The only difference is that now it's a sequence decoder. Okay, it's like one after the other sequence goes in, x1, x2, x3 goes in, and these means and these are produced, and then from there you sample a Z from there, and then you kind of again pass it sequentially one after the other, and then it produces the sequence as an output. So only difference is like sequence of input and then sequence of output. So previously we had an image as it goes to the encoder, this goes to the Z, and then decoder was trying to produce the input image. Here it's about sequence being input, and output you want to reconstruct the same sequence. So so this was like the initial work, and while they were doing this, they encountered this problem, that when they were training the VAE architecture, then they realized this annealing issue, I mean the posterior collapse issue. So so obviously their paper was more about so adapt VAE for text processing basically. So that's why they are using LSTM. So they use this architecture for both encoder and decoder, obviously, and so they form a sequence autoencoder with Gaussian priors, and so basically they adapted the VAE, and they tried variations of using also some feed-forward neural networks and so on. And something similar was also tried by them, but I'm not going to a bit of detail there. But let us look into annealing part. So the quotation from their text, from their paper, is this: most training runs with most hyperparameter models that consistently set q phi z given x. So this is the encoded value equal to the prior pz, bringing KL divergence term of the cost function to 0. So this we directly quoted this issue that they faced. So then they went for annealing. So let us directly go for the annealing, the remedy part, one possible remedy. So add a variable weight to the KL term. So empirically, because there are many counter examples, that's why I use the word empirical. What they think is that KL term is to be blamed, but there are subsequent papers that came after that. They say not necessarily it's the KL term. So these are all empirical. It's so in this paper at least they went around with having this variable weight to the KL term, and at the start of the training they set the weight to 0. So basically they want to keep the role of the KL term a bit negligible in the beginning. So basically they look into the focus on the reconstruction loss first. They give importance to that, and the KL term, because in loss we had KL and reconstruction loss. So initially they go with almost no KL term during training. So that the model learns to encode as much information, a training process gradually increase this weight, forcing the model to smooth out its encoding and peg them into the prior. So that was their approach, and this is what they did in practice. So basically they start from kind of like zero KL, zero weightage for the KL term. Yes, I hope it's the correct figure. So if we look into the loss, I don't know where it is. the KL, yeah, here. So what they had, basically the idea is simple. So it may be helpful in your case if you ever try this. So basically you put a weight here, alpha, and in the initial runs, again you see the paper like for how long they keep this alpha 0 and kind of how quickly they increase this. This is something we have to verify. So initially kind of ignore this during training, and then gradually increase this alpha. So it's a simple idea. So it's a good to it's a very easy to kind of try this. So this posterior collapse was kind of initially proposed when they were trying to use this for the text and so on. Okay, so now let us look into VQVA, vector quantized thing. We had a very basic outline in the last class. So this is our VAE model, and this is with the reparameterization trick, which is kind of simple. So vector goes in, encoder is there, it produces mean and variance, and then from there we get a normal distribution. From there we sample some Z. This goes to the decoder. Decoder learns to transform the Z to some useful reconstructed image, which is very close to the input image. Okay, and this is the reconstruction loss, and this is the KL divergence term we have. And the reparameterization trick that said that that the mu and sigma that you produce, you can see this as mu plus sigma of epsilon, where epsilon is from standard normal. So that way you keep the mu and sigma, which is coming via parameterized network, separate for gradient, for back propagation basically. Because here in this case, once you sample Z from the normal distribution, you don't really know how to back prop via this, because Z came via sampling. But here if it's explicit, now Z is of this form, so I can go and propagate the gradients for via mu and sigma and so on. Okay, so this was a quick recap of VA. So VQVA says that that learning discrete latent representation. So in this case, it's not discrete. As we know, normal distribution is a continuous distribution. Continuous distribution, right? So using discrete latent representation will be useful, because in many natural problems, we need discrete, because if you look at language, languages are kind of discrete, like one word after the other. So we can see that as discrete. Speech also will be useful if we have a discrete latent representations, because speech we have like one vector representations for each of these the words, and similarly we can say for the videos and so on. So these are discrete and ordered sequences. So that was the motivation, and not just that, it could also be used in reasoning, in planning, in sequential decision making. In fact, you can use this VQVA in RNN, not RNN, I mean RL, reinforcement learning. Right? Reinforcement learning is a sequential decision making approach, right? So RNN takes a set of input sequence, and so on, right? And then it produces some output. But then there are also cases where looking at various states you are in, you would like to predict based on your given state the next set of actions that you want to take. Okay, it could be, in the basic case would be like games. You are in a current state. Your pieces are in the current state, and then based on these pieces and the opponent, and you may want to take your next move. Okay, so this is the framework of reinforcement learning, right? So environment, state, action, all this is traditionally used there. So this will be useful in reinforcement learning setting as well. Of course, I will not cover this. So again, in those cases we need some, if I have discrete latent representations that could be used. Okay, so you can see do some Google search on these applications of these later. So contributions of the VQVA paper, it introduces VQVA simple way to use discrete latents. It somehow does not suffer from posterior collapse. That was one of the interesting outcomes, I guess, because the previous list of papers that we saw, more than 10 papers all try to understand what could be the problem, but in this case they got away with that as well. Again, this is empirical. We don't know explicitly theoretically why it happens. So discrete latent variables performs as well as continuous. So one of the thing was, when I discretize the latent, then will it be as good as the continuous? But in this case they say yes, they have that. And when paired with some powerful prior samples are coherent and high quality and so on. Tested on variety of applications. They saw in this case speech and video generation. They also did it for speaker conversion. So basically convert one speaker voice to another speaker voice. So they had quite a few interesting applications in this paper. So this is the Wiki VAE architecture. It is very similar to VAE, but the only difference that you see here are these something called code book. So this is the code book. So code book has encodings of latent variables. So rather than producing a distribution Q phi z given x, and that we try to model this as normal distribution, right? So this was VAE, but what we are saying now is, no, let us map these outputs to one of these encoded vectors. Okay, whatever output we get from the encoder, it should be closest to one of the EIs here. Okay, so we can do some nearest neighbor search and so on to map these into one of the encoding. Okay, so overall intuition behind this is that if you sample from standard normal, then continuous will be like this. It can give you samples from any of these, right? And the discrete case is saying that most objects that we see in real world can be encoded in discrete form. Like, you don't need too many of these. Okay, so basically we don't see too many continuous interpolations between let's say dog and cat. We kind of have no idea between these two objects, possibilities between these two objects. But with this various z, we kind of interpolate from cat to dog, but as if our mind doesn't really make use of these intermediate ones anyway. Okay, so of course within around cat, obviously there could be different variety of cat, different variety of dog, but there is no real kind of use of all the variations that I may get from this continuous model, these intermediate objects. So this was one of the intuitions behind that. Just keep it discrete. It's also kind of efficient in that way. So the idea is simple. The vector that you produce from the encoder, it gets mapped to one of these vectors, EK. That's it. And the decoder will only use this. Okay. So that's it. So you produce couple of Z1, Z2, Z3, because you will work in a batch, let's say, and then it got picked with some of the EIs. Let us say those are here, and then it goes into to the decoder, and decoder will produce some output just based on the code book. Okay, that's it. So more precisely, the possibilities for the categorical distribution now is that we say it's one when the vector encoded by the encoder is closest to some EJ. So this is like argmin. So that's how our distribution is getting changed now. So there is a matching of the current output by the encoder with some codebook vectors, and that's it. Okay, so that's what we do. So so basically this is the encoding. That's the only thing we have to look at. Find the k for which ek matches with the z, the encoded vector, and that's our output. So there is no another thing is, during training there is no real gradient defined. Defined for this step basically. So if you look in terms of gradient descent, like, because if you have to look at the loss, right? So the way it is happening now is that ZE, the output is getting mapped to some EK, but this EK itself comes from argmin or minimum over ZE minus some EK. So as you can see, this is just checking from each of these, right? And whichever is closest. So as such, this is not a differentiable optimization problem. So I hope you agree that minimum of these ZE minus E1, ZE minus E2. So we're checking with all of these, right? ZE minus EK is the total. So this function, right? This function that checks for the minimum, that is not differentiable. Max function or min function is not differentiable as such, right? So then we get into a technical problem of how we will propagate the gradient like this, right? Because in the usual VAE, we did this reparameterization trick, and we could access the mean and the variance, and we could go and update the parameters. Now with this encoding step, how will you propagate the gradients, right? Well, one possibility is something called subgradient. So that's like the optimization thing. Instead of gradient descent, we can go for subgradient descent. So subgradient descent essentially would mean is like I have a, so there is this, so let us say minimize somewhere here, and you somehow came here while doing the gradient step at xk, and you are supposed to compute xk plus 1 from xk minus grad L xk. So you are here, but then you see there is a, it's non-differentiable step because there is a kink, there is a corner here, right? So then there are multiple ways to define a gradient here. So the subgradient descent method says it's a very simple actually. Xk plus 1 minus xk minus del L xk. Well, del L xk is very simple. What it says is like there are multiple possibilities for a gradient. Now which one to choose, right? So one basic idea is choose any one you prefer. Okay. So in this case, if I have a mod function like this, so here if you can see the possibilities for the gradients are between the interval 0, 1, right? So del f, so this is my function f, del f at 0 is the set of all possible tangents I can draw. So basically this one, so basically slopes are 0 to 1. So subgradient descent method says pick any one of these slopes and put it here. Okay. So one possibility for us is that this as such is a non-differentiable function, so we may use subgradient method as well. Or what they tried in this case is they say that it's approximated similar to straight through gradient estimator. So basically the gradient from the decoder, which is let's say decoder input ZQX, are just copied to the encoder output ZEX. So I will write down the loss function, so then you can see. One could also use subgradient, then like I have said. So this is the loss function they have. So you can see this is the reconstruction part, right? So basically from ZQ you reconstruct the X, and then these are the two terms that they have. Okay, and they define this as stop gradient here. So basically no gradients are taken through this. Okay, and then stop gradient E here means no gradients are taken through this. So they have these two terms in their loss, and whenever we have to do a gradient propagation, we just don't do anything here or anything here. Okay, so there is in one of the assignments that you did, there is something called detach, if you recall, in one of the assignments. So that's when you say that, okay, I guess it was in the GAN where you had discriminator loss, but when you are training the generator, then you don't really see the discriminator, the first term of the discriminator, so you detach in that case, right? So you may implement these things like so. So what they did is a bit heuristic. They did not go for subgradient idea. They kind of use this loss, and they just detach these steps. So a slight variation of this is VQ GAN. So I will give you some code, assignment to implement this VQVAE. Then you will see explicitly how to train this. Okay, so let us leave that for detail for assignment. One simple extension of this is VQGAN. In VQGAN, you just add a discriminator. That's all. Everything is VQVAE. Okay, so you can think of everything like here as VQVAE. So basically, let us focus just this part. So this part is nothing but VAE, okay, and with quantization, of course. So this is like VQVAE. So we have encoder, and this gets mapped to code books, and these code books are used by the decoder to generate the images. And these code books are like this. We have already seen. But there is an additional layer of this discriminator. So basically, this whole VQVAE, the encoder plus decoder, is seen as generator block now. Okay. So it is trying to get an input image and try to reconstruct, but whatever image it produces, there is a discriminator added now as an additional step to do some additional check that the quality of the image that is reconstructed is good or not. Okay, so that's it. That's the only thing we have. So then you, in this case, you see this as G and D, and use the loss that you have. You may use the Wasserstein also loss, or the classical classifier loss in the classical GAN. So that's it. So it seems to improve the VQVAE output. VQVAE has been used for motion generation also. We will see this upcoming classes. In detail, the video generation also. I will postpone it to the next. So in motion generation is obviously like, can you generate a motion that a person is kneeling on the ground? So these are the sequence of steps you are supposed to produce. Or can you translate this motion to text? Say a person kicks 2 times on his left and kicks forward 2 times. So all this interesting cool stuff can be done with VQVAE. Basically, you have to do something like this. So you have motion encoder and motion decoder. So motion encoder takes these and put this into code book, and this code book obviously maintains the sequence, and then the decoder takes it back and tries to generate the sequence that you are looking for. So this encoder and decoder obviously architecture, you may kind of, it's your choice. Now these days transformers are quite popular for this thing, so one may use this. So I guess I will stop for today, and we will continue with VQVAE for one more class, and then we'll go for other things. Okay, thank you.